So here I want to provide a brief overview of my project, which is on reactive simulations of the polymer to ceramic route for polysiloxane-derived SiCO ceramics. So here it provides some material properties of SiCOs, which depend on composition, namely on the amount of carbon. The amount of carbon can be tailored by using specific polysiloxanes, namely those with higher carbon contents. If the carbon content is high enough, you can actually see a phase separation resulting in a glassy SiCO phase and a free carbon phase characterized typically as graphitic carbon in layered sheets. So using the reactive force field, we can essentially simulate reactions of the polysiloxanes resulting in the SiCO. And we'd like to do so in order to gain insight on the genesis of the free carbon phase and study mechanisms which occur during that conversion process. Using mass removal, we're able to mimic pyrolysis reactions or our simulations parallel pyrolysis reactions. So here I describe the structures I'm working with, and the method gives some more details on what exactly we're doing in terms of temperature and pressure. So for PDPHS, you have this section describing the overall transformation of a 10 nanosecond simulation. So to describe in detail what that is, here's a quick video representing 5 nanoseconds of PDPHS in which you can see the strands immediately clump into this bead of SiCO embedded in carbon. And as the hydrogen is lost in that carbon phase, it condenses into these graphitic sheets. So that's a representation for essentially what we're doing. PMHS and DVB, we look into the size effects in which we see that beyond a critical size, you see a different SiCO structure. You can see a funnel type structure for the 2x2x4 and 3x3x3 models, and you see more of sheets in the smaller model. And then we also observe some reactions which occur, atomistic reactions specifically. So this is a Kumada-like process shown here on the bottom of the middle section, which is the methyl insertion between two silicon, which eventually lead to the silicon carbon tetrahedra, or the silicon carbide phases, which can nucleate in the middle of the SiCO phase. And then finally, we have PMHS, which represents a low carbon content, so we don't see phase separation here yet in our simulations. But it's simple enough that we can look into kinetic properties such as reaction rate and activation energies. And so in conclusion, we have phase separation in PMHS, DVB, and PDPHS, and we actually have an observable genesis of free carbon phase, which we can look into with more detail and determine the mechanisms in which that happens. And then, of course, we have the reaction analyses that we can perform to determine mechanisms and kinetics of the reactions. So in the future, we'd like to study larger systems, those with over 100 atoms, 100,000 atoms. We'd also like to simulate the final SiCO and excess carbon structures to probe those further and seeing if there's any changes which occur for longer simulations. And then we'd like to study reactive atmospheres, such as in the presence of a high concentration of hydrogen. And then finally, we'd also like to develop an interatomic potential to describe SiCOH using machine learning. So that concludes my brief overview of my poster.